Hello, and welcome to the second part of your video notes on atoms, isotopes, and ions. Today we're going to talk about what is isotopic notation, what is an isotope, and what happens when you change the number of subatomic particles. We're also going to talk about the mass and what the mass of the molecular, or not the molecular, the atomic mass actually is. Okay, so without further ado, isotopic notation is what we use to talk about an atom in terms of not only its symbol and how many protons it has, but also what it weighs. So that's what an isotope is, and maybe I'll write that over here. An isotope, and I'll write it in red because it's definition, is an atom. Well, isotopes are atoms of the same element, but they have different masses. So they act the same, but they have different masses, and the reason they have different masses is because they have different numbers of neutrons, different neutrons. So the neutrons are neutral. They don't really do anything for the atom chemically, but they do change what it weighs. They do something for the atom in terms of its radioactivity, its nucleus, and how stable the nucleus is, but we'll get to that at a later date. In terms of their chemical properties, the isotope mass does not change how the atom reacts. So an isotopic notation then includes the mass, because carbon is just carbon. It acts like carbon, right? But there actually can be more than one carbon. And so I'm going to write these down here. There are actually three kinds of carbon. They're all carbon, so they all have 6 protons, and that's what this number is down here. This number down, and if you notice, if I was going to draw a line about where I'd be writing my C, this 6 is written below the line a little bit, and that's called subscript in a writing sense. And so you draw it to the left and down a little bit below the atom, just the same way that if I was going to write, how we write hydrogen has a 2, there are 2 hydrogens. This is also written what we call subscript. Okay, so but when you're talking about the number of protons, it's to the left instead of how many atoms there are to the right. And this is called the atomic number. Oops, that's my highlighter. Atomic number. Okay, so atomic number is the number of protons. And that's the it identifies the element as what it is, that it is carbon. So if I can ask you, who's atomic number 6? And you could look up at the periodic table and tell me, oh, that's carbon. Carbon has 12 protons. Okay, the number up here, though, is what we call the mass number. And it's like the mass. So we said on our front page that protons weigh about 1 atomic mass unit, and neutrons weigh about 1 atomic mass unit. And electrons are essentially negligible, meaning they have almost no mass. They have 1/1800th of an atomic mass unit. So when we talk about the mass, we only really care about the protons and neutrons. So the mass number is the sum of all of the protons and neutrons. Protons and neutrons. Okay, and it tells us essentially the mass in atomic mass units. So the idea about isotopes is, if I look here, I have 3 carbons. They're all carbon. They all act like carbon. But this one here weighs 13, this one weighs only 12, and this one actually weighs 14. Okay, so these are 3 different isotopes of carbon. And the way that we call them, so when we look at them, this is the way we write them with the 13, the 12, and the 14. What we call them is carbon 13, carbon 12, and carbon 14. So when we talk about isotopes, that's how we name them. Okay, let's talk about subatomic particles and what happens if you change them. So if you change the number of protons, of course, because the protons identify the element for what it is, you get a different element. All right, so, and the elements are arranged on the periodic table in order of their atomic protons, in order of their protons, I'm sorry, their atomic number, in order of their protons. So I'm going to start with my example here, the same example, right? And if I were to change the number of protons down here to 7, and even if I left this mass the same, and I asked you who on the periodic table is atomic number 7, you would tell me nitrogen. So this is a completely new element. If I add a proton, now I have nitrogen. If I change the number of neutrons, now I'm going to get a different isotope with a different mass because the neutrons affect the mass. A different isotope. So here if I have my, oops, why is it doing that in my pen? Carbon 13. Okay, so let's look at how many protons and neutrons this has. This has, of course, 6 protons because its atomic number is 6, right? Because this mass is 13, I can take the neutrons are equal to the total mass, right? So out of this 13, 6 of them are protons and the rest are neutrons, right? So the mass is 13, protons and neutrons each weigh 1. There are 6 protons, and so the rest of them are neutrons, so 13 minus 6 is 7 neutrons, okay? If I then change my mass, let's change it to carbon 14, I still have 6 protons, but now I have 14 minus 6, which is 8 neutrons, all right? So I get a different isotope, a different mass, a different isotope, comma, a different mass. If I change the number of neutrons. I'm going to scroll up here. All right, so that's, if I change the protons, I get a different element. If I change the neutrons, I get an isotope, a different isotope. Let's talk about the electrons. If I change the number of electrons, I get an ion. And an ion, I'm going to put this in red again, an ion is a charged atom. An atom that has a charge. And they make ionic bonds, which you might remember from 8th grade physical science. In a neutral atom, so here's where we are here. In a neutral atom, the number of protons is the same as the electrons. So you make an atom, it has a certain number of protons, and then the electrons are attracted to it magnetically, essentially. We call it electrostatically, but magnetically, like magnets. Protons are positive, electrons are negative, positives and negatives attract, right? So let's see. Let's talk. So I'm going to do the same thing. I have my carbon here, okay? And a charge, if you notice, if you remember, or even here, let's look at this example here. A charge, and with our protons too, and our electrons, the charge goes kind of in the upper right. Okay, so in this example here, there's nothing in the upper right. This is a neutral atom. And what that means is that I have 6 protons, and that means I also have 6 electrons. Oops. Electrons, 6. Okay, so my overall net charge of positives and negatives, I have 6 positives and 6 negatives, is 0. That's my net charge, okay? Let's say, though, I add, like this example down here, I'm doing carbon, I'm going to have a negative, all right? So I know I still have, right, it's still carbon, so I still have 6 protons, but my overall net charge now is -1. And what that means is I must have one extra negative. So that means I have 7 electrons. Okay, so that's extra electrons. Okay, so that is an example of what we call an anion. So ions are broken down into two names. An anion is a negative ion, so a negatively charged atom, a negative ion, an ion, and it gets that way. What it is that there are more electrons. The electrons are greater than the protons, right? You have more electrons than protons, and the way that you can get that is by adding electrons, two D's in adding electrons. Okay. Another kind of ion can be, let's say I had this carbon here. And let's say I had a 2+ charge on it, okay? So 2+, and of course I have the same number of protons. I have 6 protons, but my overall charge now is +2. That's my net charge, okay? So I cannot change the number of protons. I can't say, okay, I'm going to add 2 more protons, and that's going to be my +2. If I add 2 more protons, it's not carbon. It's going to have an atomic number of 8 then, and it's going to be oxygen. So all I can do is take away electrons. So if this is +2, that means I have 6 positives. I have 2 more positives than negatives, which means I'm going to have 4 negatives, 4 electrons. That is called a cation. It's not called cation, and it's not called anion, like onion. It's anion and cation. And a cation is a positive ion. And in that case, we have more protons. The protons outnumber the electrons. And you get that not by adding electrons, but not by adding protons, but by removing electrons. Okay? So that's where the charge comes from. That's where we get ions, cations, and anions. I'm going to underline ion here just because I had everything else underlined. Okay, so a couple of examples of changing the number of subatomic particles. This one right here, that what they want us to do is tell how many protons, neutrons, and electrons. So the protons are the atomic number. That's down here. So there are 17 protons. The neutrons come from the mass. So the mass is 35, and 17 of them are protons, and so the rest of them are neutrons. So that's 35 minus 17, and that is 18 neutrons, okay? The electrons come from the difference between the protons, 17 protons, and this one, the charge says I have an extra negative, which means I have one more negative than positive. I have one more negative than positive. If I have 17 positives, I must have 18 negatives. Example number 2 here has us determining what is the isotopic notation, and then also the number of protons, neutrons, and electrons. So if I have the first thing I want to identify in order to figure out who it is the atomic number, and atomic number 26, if I'm looking at the periodic table, is iron. Fe is iron, and I can write the atomic number down here. Let me put my pen back. (26). That's what I want. So that's my atomic number for iron. The mass of this isotope of iron is 60, and so I can write that up here. That's my mass, okay? And then it has a charge of 2+. So that's what my isotopic notation looks like. That's a funny F. I kind of like it. So now I care about how many protons, neutrons, and electrons it has. So the protons, of course, there's 26. That's my atomic number. The neutrons, are 60 minus 26. Oops, my minus in there. Minus 26 is 34 neutrons. And the electrons, because I have a 2 plus, that means I have 2 more positives than negatives, and I have 26 positives, which means I have 24 electrons, and that's how I have a 2 plus charge. Okay, I'm going to go to the next slide, and we will talk about the actual mass. Okay, here we are. I hope that works. Average atomic mass. So we talked about already how I actually have different carbons. So not all carbons weigh the same. And so what we're talking about here is the actual mass that we see. There's only one mass on the periodic table. That we call that the atomic mass, the mass of the atom. But it's actually, there's more than one mass for carbon, so it really is an average, okay? And not only is it an average, but it's an average that is takes into account how much of each mass is in the natural environment. So we call the atomic mass, oops, that's not the right one. We call it a weighted average of all the isotopes. Of all isotopes. This is terrible handwriting. I don't like these pens. So your paper has this example on it where it has carbon 12, and they wrote dash 12. I'm going to write it like this as we see it, okay? And out in the world, all of the carbons in the world, including the carbons in your body, okay, 98.89% of them weigh 12 atomic mass units. 12 atomic mass units, all right? And some of the carbons in your body weigh 13. 1.11%. 1.11% weigh about 13. Okay, we're going to keep it simple here a little bit. So if I was going to take a regular average, I'm going to put this over here, a regular average. I would take, of the mass, regular mass average, I would take, right, 12 plus 13 divided by 2, because there are 2 samples. So this is the same as saying I'm going to take 12 times 1/2, right, plus 13 times 1/2. That's essentially what I'm doing, and I hope you can see the comparison there. 12 divided by 2 and 13 divided by 2. So 12 times 1/2. So that's what that's saying is that half of my sample weighs 12 and half of my sample weighs 13. Well, all we're doing here with a weighted average, and again I'm going to put it on the side because I know that's where you have space. A weighted average is, instead of calling it 1/2, we're going to multiply it, instead of by 1/2, we're going to multiply it by its proportion of the natural environment. So we're going to take 12 times, instead of 1/2, times 98.89 out of 100, because that's a percentage, okay? And then we're going to take 13 times 1.11 out of 100, all right? And we add those together in the same way that we would have added them together if we were dividing them both by 2. And what that comes out to be is, if I do that math, I get, oops, wrong thing again. I get the 12.01 atomic mass units. Okay, and that is essentially what weighted means and what the atomic mass on the periodic table is. So it takes into account the fact that most of the carbons in the world weigh 12, and some of them weigh 13. So that's also why the atomic mass on the periodic table is not a whole number. All right, and I think for this, one thing about the mass spectrometer, which you see on your sheet, is that's how we actually figure out what the percentages are. And maybe we'll do that in class together one day. But in terms of taking the notes, we're going to stop right here and call it good. Okay, thank you for listening.